the length of a curve, curvature, the tangent vector, the unit tangent vector, the unit normal vector, and the unit binormal vector. And I think it's the last new topic of this course. On Tuesday, we will be having a review, and on Thursday, we'll having exam number 4. And after that, we'll have a couple of reviews for the whole class material. So here, what do we call the length of a curve? We suppose that we have a curve defined by r of t equals x of t, y of t, z of t. That's how we define a curve in the space with one parameter t. And we are assuming that we have a less than t less than b. So we are studying this curve for t between the numbers a and b. What we call the length of the curve here is the quantity that can be computed via the formula L equals integral from a to b of the magnitude of v of t dt. And we did these computations last time to see the magnitude of v of t is x prime squared, y prime squared, z prime squared dt. Joanne's example here, you might have r of t equals cosine t, sine t, and 1. You get r prime of t is negative sine t, cosine t, 0. The magnitude of r prime of t, square root of negative sine t squared plus cosine t squared plus 0 squared, and that's square root of sine squared t plus cosine squared t, and that's 1. So the magnitude of r prime of t here being 1, L equals integral here 0 less than or equal to t less than or equal to 2 pi, 0 to 2 pi of 1 dt. And the integral of 1 is t, 0 to 2 pi. So the length of this curve is 2 pi. By the way, when you look at that, this is actually a circle. When you restrict it to the xy plane. So it is a circle in the xy plane, so not in the xy plane, in a plane that is parallel to the xy plane at z equal 1, right? And you know that the perimeter of a circle is, what's the formula for the perimeter of a circle? Two pi times the radius. And this radius here is 1. That's why you get that, okay? in general, let us prove the formula for the length of a circle, or say the length of an arc of a circle. Let's say we have r of t equals r cosine t, r sine t. That's a circle, and now we restrict theta and the angle 0 between t between 0 and the angle alpha. So that means we are looking at the arc. The radius here is r, and the arc is of angle alpha. And we are looking for the length of this arc. Okay. And so you would say r prime of t is negative r sine t, r cosine t. The magnitude of r prime of t is square root of negative r sine t squared plus r cosine t squared, which is equal to square root of r squared times cosine squared t plus sine squared t. And this sum is 1, and that square root is equal to r. So L equals integral 0 to alpha of r dt, which is rt, plug in 0 then alpha. So you get r times alpha. So the length of this arc is nothing but the radius times the angle alpha.
Will that angle be in radians or degrees?
Radians, always. And which brings you back to this other formula, because when alpha is 2 pi, it's the whole thing. It's 2 pi r. And in this example, that was 2 pi r with r equal 1, right? All right, so on B, let's say we want to have the unit tangent vector. So the unit tangent vector is defined as t equals v over the magnitude of v, which is r prime, because v is r prime, divided by the magnitude of r prime of t. So the unit tangent vector is the vector of magnitude 1 in the direction of v. V being the velocity. In our example 1, and we computed the magnitude of r prime, it was 1. So that's what the unit tangent vector is in this case. In the example 2, we had r of t, r cosine t, r sine t. We got v of t equals negative r sine t, r cosine t, and t is v over the magnitude of v, and that is negative r sine t, r cosine t, divided by, and we computed that magnitude. In this case, we found it was r. And so you divide each of the components by that r, you get the vector negative sine t, cosine t. So in this case, t is the vector negative sine t, cosine t. Questions? So that's how it's done. Our next topic is the unit normal vector. We can, before getting there, first let's talk about the curvature. it's going to involve that as well. So the curvature is the quantity kappa that will be defined as the magnitude of t prime, where t prime is the derivative of the unit tangent vector divided by magnitude of v. Which is also the magnitude of r prime. Okay. If we take our example 1, in which we had cosine t, sine t, and 1, we got vector t, what's the t? Equals negative sine t, cosine t 0, and r prime, magnitude of r prime was equal to 1. So in this case, the curvature is going to be magnitude of t prime over magnitude of r prime, which means I need to take the derivative of this vector and then take the magnitude. So that'll be magnitude of, derivative of this is negative cosine t, derivative is negative sine t, and that's 0, over magnitude of r prime in this case is 1. And the magnitude of this is square root of negative cosine t squared plus negative sine t squared plus 0 squared over 1, which is nothing but 1 over 1 equal 1. So the curvature in this case is kappa equal 1. Are we good? Hello? Can you hear me?
Yeah, you can hear you.
Yep. So in example 2, we had, this was r of t. We had r of t equals r cosine t, r sine t. We got t equals negative sine t cosine t, and the magnitude of r prime is equal to r. So the curvature is equal to the magnitude of t prime over magnitude of r prime, and this is equal to the magnitude, and you take derivative, you get negative cosine t, derivative negative sine t. Then you take the magnitude and you divide by r. And that is square root of negative cosine t squared plus negative sine t squared over r. And that top is 1 over r. So here in this problem, the curvature is kappa equals 1 over r. So for a circle defined in this way, you get that the curvature is 1 over r, where r is the radius. And now from here, we can introduce the other notion of the radius of curvature. Based on this, in general, the radius of curvature is r equal 1 over kappa in general. It gives a sense of what the radius of a circle that would approximate locally the curve is. So the more the more you are bent, the smaller that radius is going to get, right? The flatter you get, the larger that radius is going to be. Let me give you an example to explain what I just said. For a line, we define the line as r of t equals, let's say, a plus bt, c plus dt. This would be the equation of a line. Let's see what happens in this case for the curvature. What's r prime of t? R prime of t is b d, right? So magnitude of r prime of t is square root of b squared plus d squared. And the tangent, the unit tangent, is equal to r prime of t over magnitude of r prime of t, which is equal b over square root of b squared plus d squared, d over square root of b squared plus d squared. So this is the unit tangent vector for the line. And now, guess what? What's the curvature? It's equal to magnitude of t prime over magnitude of r prime. But t prime is 0, 0. Because derivative of this is 0, derivative of that is 0. Divided by magnitude of r prime, which is 0. So for a line, the curvature is 0, which leads to the radius of curvature 1 over kappa going to infinity, explaining what I was saying, that the flatter you get, the larger the radius of curvature. Does that make sense? That's why sometimes we do say that the radius of curvature here gives you approximately the radius of the circle that would approximate locally that curve. If I want to put a circle to approximate locally this thing, that radius has to go very far because it's flat. It's not bent, right? And you can see for the circle, for the circle right here, I computed that example, and you see that the curvature is 1 over the radius of the circle. So the radius of curvature in this case is exactly equal to the radius of the circle, right? That's a perfect case. When you have a circle, you're moving along a circle, the best approximation in the neighborhood of any point is the same circle that you're moving along, right? That's why the radius of curvature is equal to the radius of the circle that you're moving on. Any questions? Yeah. Let's see another example. Let's say we have r of t equals 2t squared t cubed. No, man. Let's say just t, because if we go further, we might be in trouble with derivatives and so. So let's say we have this r of t, and we ask what is the curvature and what is the radius of curvature. Then you would say you start by finding that tangent line. So r prime of t, in this case is 4t and 1. So the magnitude of r prime of t is square root of 16 t squared plus 1. And that implies that t is 4t over square root of 16t squared plus 1. 1 over square root of 16t squared plus 1. So that's the unit tangent vector. And now you'll begin to see how ugly those things can actually get when you try to compute them. Let's see, here we want to find kappa using the formula. What is kappa equal to? It's the magnitude of t prime over magnitude of r prime, right? Now, but to get the magnitude of t prime, you got to find t prime first. That's where it gets ugly, right? So what is t prime? Derivative of this, that's a ratio with square roots. And so that's going to be 4 square root of 16t squared plus 1 minus. And then you take the derivative of this one. That is 16t over square root of 16t squared plus 1. All of that divided by that square root square, 16t squared plus 1. See? Just for that first one. Times the 4t. And then the derivative of this one will be minus 16t over 16t squared plus 1. And then the power here is going to be 3/2. That's 16 t squared plus 1 raised to the power 3 house. You close that. So you can see that starting just from this simple square that you put here becomes very hard to compute those things. So probably it's better to look for an alternative method to do that. So t prime is here, when you multiply, you're going to get 16 times 4 t squared, and they cancel with the 16 times 4 t squared here. And then you have 4. So you're left with 4 here over 16t squared plus 1 to the power 3 house minus 16t over 16t squared plus 1 to the power 3 house. So that's what you get as t prime. And now if you take the magnitude of t prime and divide by magnitude of r prime, then the magnitude of t prime in this case is going to be the magnitude of that, which is square root of 4 squared. So I can take 4 out, so that can be 4, and then square root of 1 plus 16 t squared, because that'll be 4t squared. That's 16t squared divided by 16t squared plus 1 to the power 3 house, and then I divide it by the magnitude of r prime, which is square root of 1 plus 16t squared. So these two cancel, and you get kappa equals 4 over 16t squared plus 1 to the power 3 house. Okay. Now, because of what I just explained here, we would look for a different way of finding the curvature in this case. And then the radius of curvature in this problem is just 1 over that, right? So I can lead you 1 to r equals 16t squared plus 1 to the 3 house divided by 4. Now let us look at the alternative in this case. So the alternative formula for the curvature says that the curvature is equal to the magnitude of V cross A over the magnitude of V cubed. This is obtained after doing some simple transformations, taking derivatives. And the problem with this formula is that you can only use it when your vectors have 3 components. So if you have an example of problem in which you have only 2 components as the one that we just solved, then what you will need to do will be to add a fake component that is equal to 0. Okay? So in our problem here, with that same problem, so alternative solution. So R of t is indeed 2t squared and t. And so I'm going to change that, change to R of t equals 2t squared t 0. So I add a third component 0 to be able to have cross products, because we can only do the cross product when we have 3 components. You can't do the cross product of a vector that has only 2 components, right? So then after doing that, you find v of t, same as we did before, that's 4t1 0, and a of t, which is the derivative of v of t, that's 4 0 0. That's it. And so v cross a is equal, you take this vector, cross product with that, and that's the way we did it. Cover the first one, you get 1 minus 0 0. Cover the second one, you get 0 minus 0 0. Cover the third one, you get minus 4. So that's the cross product, and the magnitude of the cross product is square root of 0 squared plus 0 squared plus minus 4 squared, which is 4. And that leads to magnitude of r prime of t, same, square root of 16 t squared plus 1. So kappa of t is magnitude of v cross a over magnitude of r prime, which is v cubed, equal magnitude of v cross a over v cubed, equal, and that is v. So that's 4 over 16 t squared plus 1 to the power 3 halves. And now you take that answer and you compare to the answer that we got here. Is it different?
It's the same.
It's the same, but you see how much work was done here with all those derivatives to get this, while in this answer, all we did was get that cross product and divide, right? So it's a very effective way of answering the question when you have that R of t and you can easily find those derivatives and do this. Any questions? Is there any question? Okay. If not, now let's attack the unit normal vector. That's n equal, and the unit normal vector is defined as the magnitude, sorry, not the magnitude, but t prime first divided by the magnitude of t prime. So first of all, you take the unit tangent vector, you take its derivative, and then you take the magnitude and you divide. There you go. And you got n. And notice that this vector is orthogonal to t. So it's a vector that forms an angle 90 degrees with the tangent vector. Why is that? Because n dot t is equal to t prime dot t over magnitude of t prime, and this is 1/2 derivative with respect to t of t dot t divided by magnitude of t prime, and t dot t is 1 because t is a unit vector. And derivative of 1 is 0. So that's why n dot t equals 0. That implies you have an angle of 90 degrees between n and t. Any questions? In first example, we had r of t cosine t sine t1. We got t. What was our t equal to? Negative sine t cosine t0. And the magnitude. And so we got t prime is equal to negative cosine t, negative sine t 0.
Can you move the paper up a little bit? Thank you.
And here we can get magnitude of t prime is also equal to square root of negative cosine t squared, negative sine t squared plus 0 squared. That is 1. So the normal vector, the unit normal vector n of t is t prime over magnitude of t prime in this case equals negative cosine t, negative sine t 0 over 1. So that's what the unit normal vector, the principal unit normal vector is in this case. Now, anytime we are able to define this, get the normal, get the tangent line, given that we can see now that the normal vector and the tangent vector, the unit normal vector and the unit tangent vector are orthogonal, we might want to find the components of the acceleration on those axes. You remember when we were talking about motion in the space, we had to take the acceleration on the various components and integrate them to get the velocity, and then integrate to get the vector position. So here we might want to do the same work in this case using the new system of vectors that we will get. So we get here the one, it's part of D, so normal component of the acceleration. What we call the normal component of the acceleration is an. It's not a vector, it's a scalar. And I would say it's the acceleration dot product with the normal. You can do that. You can do this computation to get it. If you know the normal vector and you know the acceleration, you can do the dot product to get the normal component of the acceleration. Otherwise, if you have the curvature, you can also say the normal component of the acceleration is the curvature times magnitude of r prime squared, or times magnitude of v squared. So the normal component of the acceleration, when you know the velocity and the curvature, you can just say it's the curvature times the magnitude of v squared. If you don't know them and you know the acceleration and the normal, you can just do a dot n. If you know the radius of curvature, this is also equal to v squared over r, because the curvature is 1 over r. So you can use any of these formulas to get it. So in the example that we just solved here, let me finish first and then I'll get back to some examples. And there is also what we call the tangential component of the acceleration. A t, it's equal to the acceleration dot product with the tangent, with the unit tangent. If you know just the velocity, then you can also say that it's the magnitude of v prime So if you just take the derivative of the speed, you get the tangential component of the acceleration. If you just take the acceleration dot product with t, you get that same quantity. Do we have any questions at this point? Now, let me give you this problem. Find AN and AT. I'm giving you time to answer this. All right. What you got there, Nick?
I am about halfway through. I got A of t though, so I can do that.
Okay, let's go.
So for A of t, first I found t, which is the v over the magnitude of v, and which is r prime over the magnitude of r prime. So then I found r prime to be 1 and 2t for the two components.
Mm-hmm.
And then the magnitude of r prime was the square root of 1 squared plus 4t squared.
Mm-hmm.
And then I divided 1 and 2t in the components over that and found t to be 1 over root 4t squared plus 1 and 2t over root 4t squared plus 1.
That's it. Okay.
And then I found a, which was the derivative of v, and I found that to be 0 and 2 for the components.
That's it. Very simple. And so?
And then a dot t was 0 plus 4t over root 4t squared plus 1.
That would be, first of all, just write this. That's 0, 2 dot 1 over 1 plus 4t squared. So it should be pretty straightforward when you look at those steps. Just write down what is necessary. That's it. And then now you do the dot product. That's 0 plus that. That's 4t over square root of 1 plus 4t squared. So that's it. This is the component. What about the other one? What about an?
I hadn't gotten to that one yet.
All right. So let's look at the formulas that are given. You have a dot n, but to do a dot n, you need to have n as well, right? So that looks to me like a long shot. So what's the alternative that you have? What's the alternative you have for an?
The magnitude of velocity squared over r.
Magnitude of? Now, if you want to go that path, it's gonna give you a lot more work, I think. You have v, oh, and well, I get what you're saying. So now it's kappa times the magnitude of v squared. So what you need to think about is how to get kappa, which is the curvature. How to get the curvature in this case. So we can do this. And then to get kappa, we know it is the magnitude of A cross V over what? The magnitude of V cubed, right? And that implies that AN is also magnitude of A cross V over magnitude of V, because times magnitude of V squared. So you would have this alternative as well for the normal component of the acceleration, right? And that's easy to do. You have V, you have A, and all you need to do is add the zero component to have 3 by 3 vectors, So you're gonna say V is where was that? V 1 2t, and then we add the 0. A is 0 2, and then we add the 0. So we got V cross A. That's gonna be 0 0 and 2. So that's V cross A, and the magnitude of V cross A is therefore square root of 0 squared plus 0 squared plus 2 squared, which is 2. And that makes it the normal component of the acceleration equals 2 over the magnitude of V, which is square root of 1 plus 4t squared. You see how simple it turns to be. But if you want to go with the other formula, then you will have to take the derivative of t, right? And it's going to give you a lot more work than just this. Any questions on this? Now, when you're free, you might want to check this. That A equals AT times T plus AN times N. This is not dot product, it's prosthetic product. It's just a product. So you might want to check that. You have A, you have AT, you have T, you have AN, you have N. And sometimes this formula is actually also used to find N. Like in this problem, for example, I have already A, I have AT already, I have T, I have AN, I can solve for N. Instead of going to say N is equal to the to T prime over the magnitude of T prime, just solve this, else you get N. Now we good? Hello?
Yeah, it's good.
Is there any question? So technically we have covered everything on this topic except one last thing, which we could call the binormal vector, unit binormal vector. And so that is B equals T cross product with N, okay? So when you do that, you know that this vector B is both orthogonal to T and N. The three vectors form positively oriented orthonormal basis of the space. Meaning what? That the angle between any two of them is 90 degrees, then the length of each of them is 1. And any vector in the space can be expressed as a linear combination of B, T, and N. Now let me give you this last question. So this is technically how I will phrase this question on your assignment. Find T, A, V, kappa, A, N, and A, T. We have not that much time left, just try with you. All right, let's see the first one, how we get T.
To get T, you have to define V first. So you take the derivative of R of T, which is equal to 1, 6T, and then 1 for the components.
So that's V of T. And the magnitude of this is
root of 36T squared plus 2.
That's it. And so T is 1 over root 2 plus 36T squared. 6T over root 2 plus 36T squared. 1 over root 2 plus 36T squared. So that's T. And how we find A?
You have to take the derivative of v.
That is.
So 0, 6, and 0.
So that's it. So now you got T, A, V, and how we get kappa now?
Would you do a cross v over v cubed?
That's the thing. So if you don't do that, you try anything else, you're gonna be spending hours on this problem and studying that the exam was long. So here you take A cross V. We got A and we got V. So we can put that V right on top of this guy. That's 161. Now we can do that cross product. If we cover this, we get 6. We cover this, we get 0. And we cover that, we get 6, right? So that is minus 6, 0, 6. And the square root of those squares, that's magnitude of A cross V over magnitude of V cubed. And that is equal to 6 root 2 over magnitude of V, that's here, 2 plus 36 t squared to the power 3 halves. That's what you will get for the curvature. And then AN, you say it's magnitude of A cross V over magnitude of V, right?
Yeah.
So that's again, in this case, it's gonna be 6 root 2 over square root of 2 plus 36 t squared. And then AT, how you get AT?
A dot t.
A dot t, so that's it. And this is A, that is t. When you dot product 0, 0, 0, 0, you're left with 6 times 6. That's 6 times 6, 36t. 36t over square root of 2 plus 36t squared. And you can solve this problem in like 6 minutes, right? And do all of that just by using those alternative formulas. Thank you. That's the end for today. See you next time.
Thank you, Dr. Longwell.
See you. Thanks. Thank you, guys.